High Store Pore project is really looking at the kind of fundamental processes that are going to be at play during the large-scale hydrogen storage in porous rocks. So our focus is on porous rocks. There are other options for underground storage, such as salt caverns, but the High Store project in particular is looking at porous rocks, and that's really what I'm going to focus this talk on today. So yeah, I'm part of a team, an extensive team here at Edinburgh, and also at other universities across the UK. So we have Gillian Pickup from Heriot-Watt, we have Sam Cleaver from Imperial, and we have Leslie Mabons from SANS, which is our sort of Scottish Association of Marine Science. So we have a really a great group of researchers at various stages of their careers, from PhD students to very established professors. So we have a really dynamic and interesting team. So I'm really delighted to share with you some of the findings from all of our work. So without further ado, I think we all know why we need to be here. Our greenhouse gases are too high, and energy contributes a very significant part of that. So the energy in total is nearly 3/4 of the greenhouse gas emissions by sectors. So it's really important that we do something to try to tackle the decarbonisation of energy, be that for transport, for heating, for any of these aspects. And one of the potential pathways to reduce that, I mean, we're making great progress with renewable energy and energy efficiency, and we are making progress. But some of these industries are very difficult. They really do require deep decarbonisation. And hydrogen has been suggested or is certainly being mooted as a potential pathway. And there's a lot of activity and pilot projects looking at hydrogen as a sort of pathway to decarbonise a significant number of these energy sectors. It can decarbonise our heating by replacing natural gas. It can decarbonise our decarbonise transport. So there's a lot of options with hydrogen. It's a very flexible low carbon alternative. So currently, so if we look at just our current production of hydrogen, we have various different types of hydrogen, and I'm sure you all know this. We have our grey hydrogen, which is the one that we're really more familiar with, and that's really from hydrocarbon based. So it's stream reformation or any of these other sort of alternatives of extracting hydrogen from hydrocarbons. The problem with that is that it produces a lot of CO2. I think you get about 7 times as much CO2 as you do hydrogen from a lot of these processes. So it's not really a low carbon alternative as it currently stands. For it to kind of move forward, we're going to really need to either combine that CO2 with CCS and capture that CO2, or of course the other alternative is to generate our hydrogen from renewable energy using electrolysis, and that's the sort of true way forward that we're keen to explore. And using our kind of renewable energy. But at the moment, that's really only about 5% of the current world production. The rest of it is grey hydrogen from hydrocarbon based. But this is something that will move forward in the future. And actually, when I was getting ready for this presentation, I just wanted to know how much hydrogen was being produced at the moment. And I did a sort of energy equivalent calculation. And so we're producing roughly just over 2,000 terawatt hours of energy in the hydrogen that we produce for our ammonia and all the other industrial uses it's currently produced from. And to put that in context, that's well in excess of the entire UK annual energy consumption, which is 1,660 terawatt hours. So that kind of puts it in an interesting context in that actually we're already producing enough hydrogen to power the UK. So we're certainly looking at being able to upscale this existing production. So I thought it was interesting, and I hope you do too. That you're aware of that. So the key with hydrogen, of course, is that it does have this high energy density by mass, and that's what makes it a very powerful kind of energy vector. But on the other side, it's got a very small mass by volume. Which means that it's really quite challenging to store. And even when we liquefy it, its energy density doesn't come close to that of petrol or any of the sort of hydrocarbons. So the key really is that for hydrogen, for decarbonisation, we're really going to require large volumes of storage, really large volumes of storage. And that's where the High Store Pore project comes in, because one of the, well, I'll show you on the next slide. Actually, you'll see really how much capacity the geological storage can provide in the story of hydrogen. So I normally do this as a little quiz, but I thought I'd better keep it simple. But it's really important. So if I'm sorry, this is a little bit UK centric, but if we are to consider the scale of storage we need, so if we take, for example, Scotland, which is where I'm from, if we think about the amount of hydrogen that we need to just replace Scotland's heat. Now, I think most of you will know that Scotland's a pretty cold place, so we do use a lot of heating in the winter. So this is just a sort of equivalent calculation for how much hydrogen storage we would need if we were to be able to store that entire amount to heat Scotland. So traditionally, a lot of our gas in the network is stored as line packing. So you kind of you inflate the pressure of your pipe system, and you can store a little bit higher density gas. So if we were to put that into our existing system to store that amount of hydrogen, we're going to need 2 million kilometers of pipe at standard 70 bar and 25 degrees centigrade. So that's quite a lot of pipe work to do any line packing. So that's not really a feasible option at the scales that we need. We would also need 40,000 swimming pool sized tanks. Again, these are held at 100 bar and 25 degrees centigrade. So it's not impossible, but it's certainly, I'm not so sure people will want these sort of big surface tanks sort of dotted around the country. So again, we're going to need 40,000 of those, which is a fair number. Salt caverns, of course, are a very important route, and they're definitely going to be one of the kind of key enablers for hydrogen in the early days, because these are quite accessible and proven gas storage technologies that we are very comfortable with using. So for Scotland, we would need 230 salt caverns. The drawback, of course, with salt caverns is that they are geographically limited in their locations. So there's not that many places that the correct geology is in place. And then to put that in context, that just all of that can be stored in one offshore field. So the Rough gas field is the example I used, and that's the kind of decommissioned gas storage site for the UK. This is where we used to store our natural gas for use in the winter months. So we only need one of those fields for the equivalent of 2 million kilometers of line packing. So that really puts it in context as to what geological storage can provide for the hydrogen economy and really enable that upscaling of it. So yes, I think it's just important to see that in context, and also to reiterate why the geological storage is so relevant within this story. Which brings me on to the HyStorPor project. So this is a project that's sponsored or funded by the UK government. So they certainly have made a strong commitment to looking into the feasibility of hydrogen, and there's a large number of pilot projects underway in a number of countries across the world, actually, all of which are kind of feeding into this. And as we upscale it, people are starting to recognize more and more that the storage is at the moment kind of one of the limiting factors. So our goal really is to understand that geological storage. So what we're really wanting to do is we want to identify if, when we store the hydrogen in the subsurface, are there going to be any chemical or microbiology reactions between the rocks, the fluids, the cushion gases, and the hydrogen that may compromise the storage site or damage the storage site in any way? So we really want to understand what's going to happen in the reservoir when the hydrogen is stored. We also want to understand these flow processes. So to make sure that we can get in what we get out, we can get out what we put in, and vice versa. So we want to kind of understand whether any of the trapping mechanisms, the solubility, all of these kind of aspects of how the hydrogen will flow within the subsurface, how it will migrate, how it will collect under the sealing rocks. So that's a really big important part of the HyStorPor project. And then of course we have to take all that knowledge that we're getting at the lab scale and at the local scale and really put that into the reservoir scale. So we'll also be undertaking a lot of reservoir simulation, both to kind of benchmark and enable the experimental work to be upscaled, but also to really understand that store, recovery, volumes, injection rates, location of wells, all of this sort of reservoir engineering of the system, and we're also investigating that. So it's a pretty wide scoped project. And what's crucial is understanding where hydrogen sits in people's opinion, and how they see hydrogen fitting into that story of the low carbon and emissions mitigation, and really clarifying what people and opinion makers and policy makers really think about hydrogen and hydrogen storage as a future pathway. Because if we bring everybody with us and kind of just make hydrogen every day, make it a little bit normalize it, then this is a really important thing that goes hand in hand with the research, because you need to really have both of those. You need to have the research, but you also need to bring everybody with you on that journey and get their support. So the High Store project also is undertaking some work to really clarify these societal views on hydrogen. So that's the kind of project goals in a nutshell. It's an ambitious project, but I hope I can show you that we're making really interesting progress and fulfilling some of those ambitions through the talk. So our project setup, we have a very engaged and rather fantastic advisory board. So the key really is those links very much between industry and ourselves and academia. I mean, most of the people on our board are actively working within the hydrogen scope, within the hydrogen sort of economy field, and it's important that we can make sure that there's a sort of feed in of information between the two. So our advisory board are very valued members of the High Store Port team. And then the research itself, well, that's broken up into kind of work packages, we call them, and each work package deals with one of those different goals. So we have one work package looking at the chemistry and the biology, one looking at the fluid flow, one looking at the reservoir simulation, and of course, one looking at the public and stakeholder information understandings. And we're trying to make sure that we anchor our research really and our experiments and our modeling onto real sites and samples. And that's really where that industry link also comes in and becomes very important to make sure that we're making our research as applied and useful as possible. And then, of course, we have our dissemination pathways to impact. So we're lucky to have SCCS, which is a sort of dissemination and public stakeholder organisation based in Scotland. And they help us link between industry, government and researchers. Obviously, as academics, we're doing our papers and our workshops and talks like this one to disseminate our findings. And we also want to engage with the public and sort of NGOs and policymakers as well. So that's very much kind of that whole setup of the project is linking industry, research, and then of course dissemination and pathways to impact to make sure that we can get that message out as quickly as we can. So now I'm going to delve into the science a little bit, which is we've got some really exciting outcomes from the work that we've been doing so far in the first year of the project. So I'm just going to kind of give you a quick summary from each of the work packages, and just to give you some of the kind of key findings that we're seeing even at these early stages in the story of hydrogen storage in porous media. So within work package 1, we have kind of 3 different tasks. The first one is the microbial processes. Now I know Marcus gave a fantastic talk on that a couple of weeks ago. So anyone who saw that will be very familiar with what's happening there. So I won't in any way repeat what Marcus has said, but I will kind of highlight what we're finding. We haven't done any. So I'll present some of our thoughts on that and our findings from reviewing the subsurface conditions. We're undertaking some experimental reactions of hydrogen with the rock and brine. So we're really just trying to develop equipment which basically recreates the conditions that we have in the subsurface, both in terms of pressure and temperature and stress. And then we can really basically just, it takes a window into what's happening, and we can see these reactions happening as they occur, and that gives us an idea of what happens. And one of the important things when you're working kind of experimentally is often the scale is very small. So what we really need to do is try to bring that up to either different time scales or different spatial scales. And one way of doing that is through our sort of upscaling into modeling. So a lot of work will be based on benchmarking our models against the experimental work so that we increase the confidence in our geochemical modeling, so that we really test the robustness of the existing modeling packages, so that we can be confident that the outputs from the modeling are representative of what's happening in these hydrogen storage reservoirs. So that's a really important kind of thread of information about that, benchmarking experiments, and then trying to kind of make sure the models are robust enough and then use them to answer the questions. So that's our first work package. So I'm just going to just introduce you to some of the findings that we've had. So of course, as Marcus will have told you about, I mean, they're using it for a different purpose. They're using it for methane generation. Of course, in a hydrogen storage site, we don't really want to lose any of our hydrogen for methane. So we're kind of sitting here in the sort of opposite situation, in that we want to really minimize that production of methane, and we don't want to be losing any of our hydrogen. So we don't want any, we want to minimize chances for consumption of hydrogen. We want to minimize any precipitation of iron sulfides or souring of any of our stored gas with hydrogen sulfide, or any of the microbial induced corrosion and biofilm blocking. So these are the kind of ideas that we want to understand, because all of these can impact on the reservoir. So biofilms can kind of, they can reduce our injectivity. As I say, we can contaminate our production gases. We can damage our topside facilities. So really, we need to get a handle on these microbial activities and make sure that we understand their limits, so that we can kind of work within those limits. And it's understanding those limits of sort of happy bugs, as I'll call it. If we understand where the bugs are happy and not happy, then maybe we can kind of use that to as a site selection tool. So one of my colleagues at Edinburgh University, Katriona, she's been doing some really excellent work on understanding these limits. So if I move on, so she's been really assessing three major types of microorganisms that use hydrogen in the subsurface. So the methanogens, who like to eat hydrogen and produce methane. So that's the one that Marcus will have been telling you about. The Homo acetogens, I'm not very good as a biologist, so these produce acetate as a metabolic byproduct. And of course, we've got our sulfur species reducing microorganisms. And again, all of these either will contaminate or consume hydrogen, and we want to kind of minimize those. So I won't zoom in on the images, but the slides will be available for you if you're interested. But basically what ICA's done is gathered together the temperature ranges, the pH ranges, and the salinity ranges that these different microorganisms are comfortable in, that they grow under and they flourish, so that we can start to get a handle on these sort of limits of where you see these bugs who are thriving and bugs who are limited. So ICA's work has really discovered that there are limits in the sort of salinity, in the temperature, and the pH that these bacteria are comfortable within. So we know that, for example, at over 122 degrees, very few of the microorganisms are happy. So that means that if you've got a reservoir above that temperature, then you're going to inhibit some of that activity. pH, again, the most of them prefer a kind of pretty neutral pH. And then the salinity was the last area that we looked at. And anything above 5.8 molar mass of salinity or NaCl equivalent, then these bacteria are not going to be happy. So we now know where that sits. So on the graph, which I know is very difficult to see, we have plotted sort of 30 or 42 of our depleted UK North Sea gas fields. So we've plotted their temperature, their salinity, and their pH. And we've also plotted in 5 storage test sites that are currently kind of being used or investigated. So we've tried to identify whether any of these fall out with the range that where the unfavorable to microbial growth. And even amongst those small number of fields that we've looked at in the North Sea, we've already identified that 7 of those fields can be considered to be unfavorable to microbial growth. And actually only 6 fields are in that kind of optimum area where you probably wouldn't want to use those fields, because if you're going to get any microorganism activity, it's going to be within those fields. So I think this is a really interesting piece of work that ICA's done, and we're just writing up that we've just put a paper in for review. So hopefully you'll be able to get access to that information pretty quickly as it makes its way through the review process. And of course, what we can do with that information is that we can then understand these critical ranges of salinity and temperature, certainly the two that we've identified as the most important. And then we can kind of quite confidently at the moment say that storing hydrogen at temperatures above 120 degrees and in salinities of above 5.8 molar mass for NaCl equivalent, you're definitely minimizing your bacterial activity. And we can almost use this as a site selection tool. So I think this is a really interesting, an interesting piece of work where already we're seeing a good number of fields in the North Sea fall out with that range. So if you're going to choose one over the other, then you know it's very sensible to choose one where your temperature and salinity are unfavorable. We do recognise, and I don't know if Marcus is online, but we do recognise there's a limitation to our analysis because, of course, the data is based on cultivated species, and of course, it's not based on hydrogen storage. It's based on sort of ecology research. So we might not necessarily have data directly from hydrocarbon reservoirs, and of course, that may change things. But certainly, this is our first pass estimate is that we have got you know, indications are that we can use temperature and salinity as a site selection tool to optimize hydrogen storage and minimize those losses of hydrogen to microbiological activity. So that's definitely an interesting finding from the first year. And of course, the geochemistry, that's a hugely important area. How's the hydrogen going to react with the pore fluids and the minerals within the reservoir? It's definitely going to like the carbonates and the sulfides and the anhydrites. It may cause clay swelling. We may get sort of feldspar and clay mineral dissolution. We've got these balances, some of them enhancing permeability, some of them reducing permeability, some of them also mobilizing toxic metals, forming toxic gases, again, which may contaminate the production stream and degrade our operational. So similar to the microbiology, we really want to kind of get a handle on these reactions and interreactions that you see between them to make sure that we're putting ourselves in a situation that if we can find reservoirs which don't have so much of this mineral to minimize these risks, then that's really what we're trying to do. So we're really trying to kind of identify these key reactions that are going to be detrimental, or indeed possibly ones that might help in the storage site. And it's really, again, it's just another way of trying to screen and optimize our site selection and really understand these fundamental processes. So my colleague, again at Edinburgh University, Ali Hassan, Ali, your surname is too long. Ali's on the call, so you can ask him these questions later. But certainly, Ali's built this fantastic set of experimental equipment, so we can run at temperatures up to reservoir temperatures, reservoir pressures, a massive range of fluid and gas mixtures, particularly hydrogen. I know you had hydrogen up at, well, I work in PSI, or up at about 55 megapascals in the lab, which luckily I wasn't there, but that can be a bit hairy, but it was all perfect. And the equipment is sealing beautifully, and we're able to do these high pressure and temperature experiments to really get a handle on exactly what's happening. And we can record the pressure and the temperature as they change. So anything happening during this time, if there's any gases being released that are changing the pressure, we can monitor that in situ. And then we can also undertake fluid chemistry and rock analysis. So we can really pick up any of these geochemical reactions that are happening within these pressure vessels. We are also developing some flow through pressure vessels as well, because these the vessels that you can see there, they're static reaction vessels, and the second year we'll be developing more kinetic reactions as well. But the batch experiments are really important for the benchmarking of the geochemistry software. So that's kind of one of the main drivers behind that. And like the bacteria we review, we have some early results. Again, I'm sorry, you probably can't see this slide very well, but at the moment we've really been developing and testing the equipment on quite generic sandstones to get our methodology right before we start using our very precious reservoir samples. So we've been using 3 different types of kind of quite clean quartz reservoirs. So we've been using, Clashak, Permian, and fell sandstone. So these are quite traditional. I'm sure anyone who works in rock mechanics or petrophysics will be very familiar with these rock types. So we've also been using them primarily because there's such a wide database on those. So having the knowledge of how they react with hydrogen can support that wide database that's already there. We do have access to real reservoir rock types. with more complex mineralogy. So we really need to start looking at the pyrites and the calcites and the anhydrites, and these are ready to test kind of moving forward. Obviously, the COVID has closed the labs for a little while and slowed down our analysis. But so we're doing our best, but we're continuing on, and we have everything ready to go. And now we're operating at full reservoir temperature and pressure. And certainly in the experiments that we've done so far, which have been quite low pressures, up to sort of 0.1 megapascal and at 50 degrees centigrade, so they haven't been at huge pressures and temperatures. But we certainly are not seeing any significant geochemical reactions. So our early indications are that there's certainly no showstoppers at the moment. And one of the important things that we'll be doing, of course, with this data is benchmarking the geochemical modelling, which we haven't really started yet. But if anybody's a geochemical modeler, then I'm very happy to talk to you guys and share these results if that's something that you're interested in doing. So yeah, but so far so good, I would say. We haven't seen anything showstoppers, and we haven't seen any significant reactions yet. What's interesting is we did do a bit of preliminary geochemistry modeling, which certainly indicated, the modeling certainly said there would be more reactions than we're seeing in the lab. So over time, we'll be able to kind of close that gap, that information gap, and really get a better understanding of what's happening with the geochemical reactions in the reservoir. But we feel quite, I think Ali and I feel quite confident nothing alarming is happening so far anyway. So that's really also good news. So then we move on to work package 2, which is our flow behavior. So again, we really do need to understand the flow of hydrogen in the reservoir. Is it going to be residually trapped? Is it going to undergo mass diffusion? You know, there's a lot of work to do in this work package, and we've broken it down into sort of different tasks to answer some of these questions. So the first one, we'll be doing our relative permeability and residual saturation experiments. So we haven't been able to get those up and running yet, but that's going to be the priority within the next few months, because this is really key data that the modelers are going to need. So we're really working to provide that data for everybody as soon as we can, because this is really crucial to provide these rel perms and residual saturation curves. We also, rather excitingly, are going to be, well, we've just finished building a X-ray CT transparent cell, so we can visualize and image the hydrogen flow through the porous rocks using X-ray micro CT. So yeah, so the cell is just ready to go, and hopefully within the next sort of 6 months. So again, that's my colleague Aika who'll be looking at that. So she's designed the flow through cell, which is going to be really cool when we get to see the hydrogen flowing through these porous rocks. So it's required, the problem with X-ray CT, as I'm sure some of you are aware, is trying to get that balance between a representative core size, but also the resolution. So you know, the smaller the core, the better the resolution. But of course, you need a slightly larger core to capture that porous network. So we've really been doing a lot of work to kind of get that optimum balance between core size and resolution, so that we can really see how that multi-phase flow through the reservoir and start to image that, and then model it once we've got it image. So another important area of the hydrogen storage system, of course, which I hadn't mentioned before, is the cushion gas. So the cushion gas is there as a pressure buffer and a buffer between the formation fluids and the working gas, the working hydrogen. So of course, there's the option to use hydrogen itself as the cushion gas, which does require quite a high capex, because you're putting a lot of that hydrogen into the reservoir and you can't get that out right until the end of the life cycle of your reservoir. Other ideas we've had are to use CO2 as our cushion gas. We're kind of quite happy. Well, we like the idea of this, because if we can use CO2 as a cushion gas, we're effectively storing CO2. We're capturing and storing the CO2, and suddenly the CO2 becomes a product. It becomes a cushion gas. But there's quite a lot of complexities with that. So we've been doing a bit of work modeling and a little bit of experimental work on that, because we would like it to be a suitable cushion gas, because it will enhance CO2 sequestration, but we recognize that there's other options, nitrogen as well. So and also the methane, of course. So we're and the natural gas. So we're starting to kind of really understand the mass transport of hydrogen and the cushion gas in these mixing zones. So we've done a bit of modelling, which I'll talk you through later. But this is, I think, quite an important aspect of the storage system. And of course, the problem at the moment is nobody really knows how much of percentage of the cushion gas. And I'm sure you're all aware that there's a very large range in the published literature about how much of the reservoir has to be cushion gas. And I've seen data ranging from 20% to 80%. So that's a big deal when you're looking at it on a scale of a reservoir. Maybe not so much in a salt cavern, which is more manageable, but certainly in a porous media, it's important. And also we want to talk about recovery efficiencies of that multiple cycles. That's a real idea of that residual trapping, because you've got this imbibition drainage cycles. So we really need to understand whether that will reduce the recovery efficiency over time of our reservoir. So we want to get a handle on that. Of course, we want to understand the sealing of our cap rocks to hydrogen. So another colleague of mine, Mark Wilkinson, he's done some calculations, some diffusion calculations, and certainly the calculations estimate that the hydrogen isn't going to be you're not going to there's not a significant risk of loss of hydrogen through diffusion in the cap rock, but we will be doing experiments to kind of support that and back these findings up. And then, like the geochemistry, the experiments will also try to benchmark the numerical modelling, just to make sure that we're increasing our confidence in the outputs from the numerical modelling. So I'm just going to quickly talk through this wonderful thermodynamic model that my colleague Ali has built. So there's a Nature paper published on this, and you can download this piece of software to do your own calculations. So basically, this is an online tool which will generate a very significant number of thermodynamic properties of hydrogen mixtures. So again, we were wanting to talk about a real reservoir where you've got existing gas, so you've got natural gas in the reservoir. You may have cushion gases, so we're still keeping CO2 in there because we're hopeful. We've got nitrogen in there as well. So we're really looking at that, and that online tool can calculate the density, viscosity, a whole range of thermodynamic properties at a range of mole fractions of hydrogen. So either from 10% hydrogen with 90% cushion gas, or 90% hydrogen, all the way through, so that you can really start to see. And that's very useful if you're talking about pipeline engineering or any of these things when you're mixing up the gas streams. We are working from pressures from 0.01 to 100 megapascals and temperatures from 200 to 500 Kelvin. So this is a really nice tool, which is freely available for anybody to use. And I do recommend, if you need to calculate a gas stream mixture density, then this is your place to go for that. So the reason why we've chosen the pressures and temperature ranges that we did is we just did a quick study of the whole hydrogen system. So we wanted to make sure that we were covering all of the temperatures and pressures that would be encountered within that range, right from the kind of transmission and generation all the way through to the storage, because we wanted this tool to be as applicable to anybody working in hydrogen as possible. So this figure just gives you an indication of why we chose the pressures and the temperatures that we did. So that's really that's that. So I'm not going to go into the equations. You want the equations, read the paper, it's fantastic. But essentially the thermobank model, it uses a combination of the Gerg equation, Gerg 2008 equation of state, and that calculates the density and a range of other properties. Now those then provide input for the supertrap model, which then allows the calculation of the viscosity and the thermal conductivity. And between those two methods, we can then have the full list of thermophysical properties from the thermal bank. And of course, the Gerg equation of state, it's based on two sides of things. It's based on your ideal gas contribution into the equation of state, and it's also based on the residuals. So it's really that each individual gas's contribution, which has to be fine-tuned and benchmarked really again through data sets. So that full benchmarking process has been gone through for the Gerg equation. So we have a high confidence in its applicability for the hydrogen system. So that's really, that's something that we can be very confident in using. So I just wanted to show you again, sorry for the slides not being so easy to read, but hopefully you'll be able to peruse them at your leisure later on when you get the slide pack. But this is just showing you some density plots for pressure, and so density over different pressure ranges for different molar fractions. So I mean, there's an infinite number of combinations that you can output from this model. So this is just one output for different temperatures. So the coloured lines reflect the different temperatures over the pressures for these different molar percents. And that's that can be generated for any of the properties. You get a table and a graphical output for that. So what's important is that the model doesn't just deal with the gas phase; it also deals with the liquid and supercritical phases as well. Obviously, in this image, we're just showing you the gas phase, which is why one of the lines on the top right-hand graph cuts off, because then it moves into its liquid phase. But the model is fully capable of dealing with the different phases that you encounter, and all that data is generated. The same for viscosity. It's just showing you another example of the viscosity outputs that you can get, so that you can find, depending on what zone what temperature range or what pressure you're working in, or how much percentage of mixing you have, you can gather this data very easily from this online tool that Ali's developed. And just to sort of reassure you that it works very well, this is the kind of validation of the outputs from the thermodynamic modelling against the experimental results. And you can see that the equation is matching them pretty spot on, with very, very small deviations from that. So we can be really confident that this GERD 2008 equation of state prediction that we've based the thermobank modelling on is working very well. So that's something that's, yeah, it's a really useful output for you all. And then the other area that we've done is we've done column heights. This is crucial for understanding the storage security. So Ali again has developed a methodology to convert pre-production, so normal column methane column heights, into hydrogen column heights. So that's based on his density difference ratio, which is the blue line on the figure to the left, and that's the density difference between water and hydrogen or methane, and that's based on his data from the thermobank. And you can see it's running pretty close to the 1. So 1-to-1 ratio. So there's not a huge difference between the density ratios of hydrogen and methane with water. If anything, it slightly moves it to a reduced column height, but that is completely offset by the dashed green line, which is showing the interfacial tension ratio. So Ali used 2 different models to calculate these, and then check them against the experimental data to double ensure, or triple check his accuracy of this data, because there isn't really that much data out there at the moment. And what you can see in this graph is that this interfacial tension ratio of hydrogen and methane and water is much, much larger than, of course, the density difference ratio. And then the column height calculation is really obtained by multiplying these two, multiplying the density and the interfacial tension ratios to produce the column height conversion factor. And that conversion factor, which is shown as the black line, that then can be applied to the existing column heights for methane. And what you can see on that graph is that it's definitely to the far side of the 1, so that we do see an increase in column height of hydrogen when compared to methane, and that increases with depth. So this again is something quite positive. So we're looking at the fact that actually hydrogen will demonstrate increased column heights, so the reservoir can sustain a higher column height of hydrogen, which is great. So the one drawback of the model at the moment is that we don't have the wettability data, but we're working on that. And again, the early indications show that that's going to also work in the favour of increasing the column heights for hydrogen. So watch this space for that one. And then our final work, well, not the final, but the work package where I'm going to talk through some of the data is our numerical simulation. So there's been some very exciting work on that. So we're wanting to really start to benchmark our experiments. We want to understand the impact of the cushion gas and the mixing. We want to look at optimizing the geological trapping structures. So we really don't understand how the geometry is going to impact the storage security. Do we need a very steeply dipping anticline to really trap it, or will it take a wider one? We need to understand that sort of buoyant flow trapping geometry. So there'll be a lot of work on that. We also want to understand the integrity of the entire reservoir to these cycles of injection, so the production and injection probably on an annual basis. So we really need to understand the mechanics and the integrity of the caprock and anything else in the reservoir while we undergo these cycles. And then, of course, we want to start looking at storage developments and understanding kind of how we optimize a hydrogen storage site. So this work is just in its infancy, but there's a couple of examples that I can show you. I hope this works. Let's have a look. So hopefully you can now see a column moving. You can see the visualization. So what we're looking at here is the injection of hydrogen in and out of a reservoir, which is fully saturated with CO2. And this is done in Eclipse. So we're using CO2 as a cushion gas, and we were wanting to look at the mixing effects. So this was a master's dissertation student, Harry, that did this with us. So this is a really nice body of work, which we're developing on. So it was a 20% porosity radial model, saturated with CO2. We injected hydrogen to begin with, and then we did these annual cycles. And what we see really is that the cyclic injection does lead to dispersion of CO2 and hydrogen over time, but precise assumptions are difficult. So this is very much a work in progress. And we do see, if I press the play again, you certainly can see that mixing zone does increase with the number of cycles. And what was interesting about this as well was that when the injection and production rates were doubled, the more mixing we got, but actually not as much as you would think. So even after 10 cycles, the final mass of produced hydrogen was producing a maximum of 1.5% CO2 from the well for the set injection. But when we doubled the injection, it was only producing 2.3% more. So double the injection, it doesn't double the amount of CO2 produced. So it looks like operational procedures, as always, will be able to be fine-tuned to minimize that gas mixing within the reservoir. And that's something that we'll be working on to really clarify and understand, because it's going to be really important. We need to minimize that mixing so that we're not risking production of or too much production of our cushion gas with our working gas. So this model, which again is another model, this is really monitoring the bottom hole pressure, and it's comparing hydrogen against methane. So this is a product. So on the bottom left of the curve, you can see that the blue line represents hydrogen and the black line represents methane through the model. So this is a simple 2D model with a dip angle of 20 degrees. So this is what I was talking to you about, the geometry. We really need to understand what happens if that dip angle changes. I think that's going to be quite important, again, for site selection and understanding what are going to be the real optimal characteristics of the storage site that we're looking to find. So this model run is running over 2 cycles of injection and production. And you can see the difference between the two. And really, there's not that much difference. They're very similar. So you get slightly elevated pressures during shut-in and production phases. We've got buoyancy dominating, but the bottom hole pressure is very similar for hydrogen and methane. So again, this is work in progress that we'll be developing and we'll be looking to share with you as time goes by. And this is a small field, a small oil field that we're building, a small depleted gas field, sorry, that we're building up. And just for interest, this really shows the simulation of the top surface. So the blue, the map that you see is basically the top surface of the reservoir. And this is just really showing you a simulation of the injection and withdrawal of hydrogen in the reservoir. And what's encouraging is that it's showing that you're certainly managing to have this kind of working gas with a recovery factor of 95%. So it's certainly, again, early indications looking that this is absolutely feasible. There's nothing untoward. So this was using the methane as the cushion gas. It was just assuming it was injecting into a depleted oil and gas field. So again, early indications are very favourable when we're modelling this the best we can. And then the last bit we've done within that is another colleague of mine from Edinburgh University, Julian. He's developed a new hydrogen storage capacity estimation methodology. So this paper is also in review. So hopefully we'll get that through review and out to you guys as soon as possible. But one of the key outcomes from this, really a very important outcome. So this is a capacity estimate methodology, and then we applied it to the UK depleted oil and gas, or depleted gas fields only. And what we wanted to do was understand if we could supply the UK supply. So the UK gas network runs through some major terminals. So those are marked in dark red on the map. So obviously that whole infrastructure is in place already. So we wanted to move those terminals and link those up and understand if we had enough storage potential. And the outcome of this study is that really we only need 3 fields to supply the whole of the UK with its gas storage requirement. We have way more potential storage than we need, just based on the existing depleted oil and gas fields. And this is great news, because actually what it's going to do is limit competition with the other subsurface activities. And that's something that we'll all be very cautious of, because we're looking at all of the subsurface for many different low carbon energy systems. So it's going to be geothermal, it'll be CCS. And what's reassuring in a way is that the hydrogen storage isn't going to take away much of the subsurface space for that. So that's also quite exciting. So unfortunately, Work Package 4 hasn't made much progress because we haven't been able to go out and do our public stakeholder workshops. But that's something that we'll do as soon as we can get back in. But it is important, and it's definitely at the forefront of all of our research. So to summarize, I'm sorry, I've maybe gone over time, sorry everyone, and I see there's questions, so thank you. But basically we think that there will be a biological site screening based on temperature and salinity, and we can choose sites that are less favourable to microbial growth. We don't see any significant geochemical reactions yet, but we've still got a bit of work to do. Our column height calculations indicate that hydrogen is going to have a higher column height than methane, and this is great. We have a high accuracy hydrogen mixture thermodynamic property estimation tool freely available for people to use. Our early modelling is showing that operational procedures will be able to be fine-tuned to minimise our gas mixing and reduce hydrogen mixing and loss, and that we have significant storage capacity in depleted gas fields, more than we could possibly need. So we're minimising that subsurface competition with other low carbon geoenergy applications. So that's everything from me. If you don't mind me getting a small plug in at the end, the High Storeport project is running an industry workshop on hydrogen, and we have some really interesting speakers lined up on the 17th of November, and the details are there. So if you want to learn more about what's happening in Scotland, in our hydrogen world, and also a little bit more about the High Storeport project, and join the dialogue on that, then you're very welcome to join us. And that is me. So thank you very much. So I'll probably stop sharing, I think. So thank you very much, everybody. An information overload.
Thank you. We'll be happy to continue and answer questions that people
Fantastic. Oh, thanks, everybody. That's great. So norm mobilization, we haven't looked at that yet. So we haven't. We have investigated the possibility of that, and I think we will add it into our geochemistry as soon as we start to get the reservoir rocks, because of course the moment the rocks we're using don't have any of the sort of organic material in it. But I think that will come as we start to use more and more realistic and complex reservoir rocks. So we will probably be looking at norm mobilization. It's not analysis equipment that's easily accessible in Edinburgh University, but we have looked into it in the past. So I think that's a good point. So I hope that we can add that too. So Osman, thank you. I am not in any way an expert on the bacteria. I don't know if Aika's online, but I don't think she is. Yes, so you're asking, when we talk about methanation, how much the ratios of hydrogen and CO2, and how much will the methane production percentage, and also what about the cost of green hydrogen in comparison with others? So absolutely. So we are. So there's quite a few questions in there in one. So we will be. We haven't built CO2 into the bacterial work at all, and I think we won't be able to in the scope of the hydrogen in the High Storeport project, unfortunately. I think ought to leave that to RAG and others to do that. Our work was very much desk-based study, although it is something we want to do, and we do have the capability to do it in Edinburgh, but it's definitely not part of the High Store Poor project. And when you're talking about the cost of green hydrogen in comparison with others, so we don't have an economic module built into the High Store Poor project, but actually, interestingly, we have another project which we've put into submission, which is looking exactly at that issue about green hydrogen. So what we're wanting to do is a whole system energy model, which is looking at the upscale that's going to be required if we were to just step change from blue hydrogen and miss that stage out completely and go from green hydrogen, go straight to green hydrogen from offshore renewables. And particularly in Scotland, we have we have a fair amount of renewable energy. And because of our grid connections, the most windy areas are actually quite far from the grid. So the idea of being able to generate hydrogen is quite attractive and might develop more sites off certainly in the north. So what we're really wanting to get a handle on is those techno-economic studies of that upscaling of green hydrogen, including the storage. So hopefully we'll be able to have an answer for you that quite shortly, because we'll take a whole system modelling approach to that. So thank you very much. And Laurent, hi Laurent. Column heights, yes. So Laurent, I tell you what, we can discuss this in detail at the High Store Poor meeting with Ali. And you can get into all of the details with that, because absolutely. I think all of these things will have been taken into account.
Thanks very much, Katriona. Great presentation. You're right, it's a bit technical, so we can.
So let's do that. Unless anyone's very interested in it, but I think
nobody will be.
Laurent is part of the High Store Poor Industrial Board, so we can talk about this at length. So Ali, heads up. Brilliant. I don't know if anyone else has any questions. That's all that was in the chat box. But thank you to you all. So sorry, I don't know if I mentioned the small the small field study that's done by one of our PhD students, Johnny Scavadi. So he's also on the call. So he's modelled the small reservoir field. So the field scale model where you saw the hydrogen being injected and withdrawal. That's Johnny's work, and he's just coming to the end of his PhD. So hopefully he'll be able to get some work published on that, and you'll be able to access some of the really interesting findings from his PhD study as well. So sorry, Johnny, but that was his work as well. So again, most people's contact details are on the slide. So if there's any area in particular that you're interested in delving into further, what I'll do is I'll add everybody's contact details for the work that they've done particularly, so that if anybody wants to continue that dialogue, then so Johnny already has his on the slides, but I'll maybe add in the individuals so that you can contact them directly and start a dialogue on that. Because I think Aika would be very interested to talk to you about all the bacterial work and things like that. So excellent.
Are there any more questions for Katriona? Well, if there aren't now, I'm sure that she'll be happy to have a dialogue with you through her contact information. And as a reminder, her webinar will be posted on the American Rock Mechanics Association's YouTube channel, so you can look for that. And with that, we thank everyone for your attendance and participation with this very interesting and exciting talk on the frontiers of hydrogen storage in porous rocks. And Katriona, thank you. And thanks everyone.
My pleasure. Thank you, Richard, for inviting me to talk. It's been a delight to chat to you all. So thanks very much.
Thank you.
Okay, take care, everyone. Thanks, Richard. So I will update the slides with everybody's contact details on them, and I'll send those to you. Hi, Evan. I'll send those to you today, later today, if that's all right.
That's just fine. Thank you.
Brilliant. Thanks, Laurent.
And how are you doing, Katriona?
I'm very well, thank you, Dan. How are you? Thanks, Laurent. I'll see you soon.
I thoroughly enjoyed your presentation. It was lovely.
Excellent.
Details, in-depth, the right balance between information and understanding for lay persons. Really, really good. It's been ages since I've seen you the last time. That was before COVID.
It was, absolutely.
But as someone who has spent the best part of several years in installing hundreds and underground caverns, I was delighted to see the work that you're doing, and I'm looking forward to see you face to face.
Absolutely.
Next year, perhaps, I don't know.
Absolutely. Well, I'm working with your team in Glasgow on the salt storage. So hopefully, at Atkins, so hopefully we'll be able to get something sort of going very soon so that we can, I'm sorry not to do justice to the salt, but the high store pour has to.
No, that's okay. No problem at all.
But yes, let's catch up soon. That would be lovely.
Take care. Nice
Take
seeing
care.
you.
Thanks.
Bye.
Excellent. Brilliant. Oh, thanks, Richard. Thank you for organizing that.
Okay. Thank you, Katriona. I'll go ahead and end the webinar, and we'll see you online another time.
Fantastic. I'll look forward to that. Take care. Thanks.
Bye.
Bye-bye. Bye. Meeting.